hopefully you see it. So yes, I'm Jānis Bikše from University of Latvia, and now I will give a talk about the groundwater level modeling using machine learning. And I will focus on temporal modeling, how to model groundwater level using different kind of machine learning algorithms. But my talk will be more I will say like a more classical presentation, but of course I will also have some codes eventually. So the next slide. Yeah. What is groundwater level? Basically, it's the depth below the ground where we can reach saturated, where we can reach where the groundwater, basically the ground is saturated with water. And the first groundwater which we can reach when we are digging a hole in the ground, that's the unconfined aquifer, which is openly exposed to the atmosphere conditions. If we dig deeper, and if we dig deep enough to reach some clay, we call these confining units, then we can reach also some deeper groundwater, which we called confined aquifers or confined groundwater. There are slightly different features for that, but in general, all that water is groundwater. And when we are talking about the shallow unconfined aquifers, then we typically say that that's the groundwater level. If we talk about deeper groundwater levels, but then we actually are not calling them levels, we are calling them groundwater heads or piezometric heads. And yeah, and that's the well where we are measuring groundwater level, and we can measure it manually, but more often, of course, we are using some data loggers to do that. And why we are measuring groundwater level, there are multiple purposes, and one of the most important one is to manage our groundwater resource. And groundwater is the main drinking water source in our countries, in Latvia, Estonia, Lithuania, and also in Poland, and of course in many other countries. And in European Union, groundwater is protected by a Water Framework Directive. So there are some obligations that we have to do with regarding groundwater monitoring to be sure that our groundwater resources are in good status. We can also detect some trends if we are measuring groundwater level. We can also analyze some historical drought or even flood events and also make some prediction for the future. For the future, we can also assess some climate change impact and also how it has already made some impacts on our groundwater resources, and also some human impacts. Like, for example, when there's a huge groundwater abstraction nearby, we can assess how it has impacted our groundwater resources. For example, in this groundwater time series from Latvia, we can clearly see the impact of the drought, which was in 2018 in Latvia. That was the largest drought event in our measured history. So we can clearly see that the groundwater levels were quite low during at the end of 2018. And what kind of tools do we have to measure or to model groundwater levels? We have these classical tools like numerical models, and most popular one is the ModFlow model, which we sometimes is called also like a gold standard. But there are also other kind of numerical models like FEFLOW, hydrogeosphere, and other models. And these are really great models. They are you can basically model their many different kind of things, not only groundwater levels, but also some pollution transport, some interaction with between different aquifers, interaction between seawater and aquifers, some human impacts, and many other kind of things. But they are quite complex, and it requires a lot of data, and also it requires quite heavy work to make these models work. And what other kind of tools do we have to model groundwater levels? There are some simplified models like Aquimod, which is developed by the British Geological Survey. These are lumped catchment groundwater models. It means that the groundwater is modeled like in zero dimension. Basically, we can say that there are no dimensions apart from the numerical models where we can have 3 dimensions. Here, there is no dimension, or at best there is 1 dimension, which is vertical dimension, and of course there's like a time, which is temporal dimension. But the idea here is that we are focusing only on groundwater level modeling, so we don't care about all the rest, about the other things. But still, in these kind of models, there are integrated multiple smaller models, we can call them like that, analytical solutions for some soil processes, some unsaturated zone processes, interaction with atmosphere, and so on. But the main focus is groundwater level. Then there are also other kind of models that works like the previous ones. For example, this one is from the France, which is developed by French Geological Survey. Basically, the idea is quite similar, but the code and the software is, of course, slightly different. Then there are data-driven approaches, purely data-driven approaches like Python package pastas, which is devoted purely to predict and model groundwater levels and groundwater heads. And it is based on transfer function noise. And this is a package which started development within the Delft Technical University in the Netherlands. And the authors, and this is open source project, so all the scripts are freely available and everyone can use it. And this package actually is getting more and more popular among the groundwater modelers, because it can use basically few parameters like precipitation, evaporation, and you even by simple parameters you can try to model groundwater levels. Of course, if you have some external stresses, for example, groundwater abstraction, you can even provide that kind of data. And the idea is that the model learns how the past events are transforming into future groundwater level. So yeah, that's the reason why it's called impulse. Also, it's called sometimes impulse response function. If you are thinking about classical groundwater modeling, not classical, but classical machine learning tools for groundwater modeling, then there can be quite a wide range of models that can be applied, and the list is really long. It's really a long list of different kind of algorithms, but as Vytautas said, quite often it's more important how do you deal with the data, how you clean the data, how you transform the data, and how you prepare the data for the model. And that's quite often the more important than to select the best model. And we are thinking about how we can, where we can use this kind of approach when we are using machine learning to model groundwater levels. We can predict some future or far future levels. We can predict at unmonitored sites, impute missing values, and assess, for example, climate change impact. So a few examples from the literature. This is how we can use the machine learning models to predict for the next few years what the groundwater levels will be. And as you can see, it's kind of reminds cross-validation strategy but it's with the rolling test validation part, where basically you are testing the data every few years for the next few years, using all the past all the data that was available up to that moment. And by doing that kind of strategy, you can create a model that can predict the future groundwater levels. You can also try to use machine learning tools to predict groundwater levels at unmonitored sites, and that's quite interesting way how to do that. And for example, this paper by Ezra Hoff, they developed a strategy where you are selecting candidate or target, they call them donor sites or donor wells, which are located in the similar geological, similar hydrological, and other kind of settings to the target site, the point where you are trying to model. And by using these donor sites, they're transforming the data in a way that can be like constructed back to like a time series for the target site. So yeah, under the hood, there is machine learning algorithms that are finding these relationships between these donor site characteristics and the target site characteristics, and making all these calculations. But eventually the result is that we can predict groundwater levels at sites where we don't have any groundwater well. Then there is this example of how we can impute or fill missing values in our dataset. This is a paper wrote by me and my colleagues, where we learned that in Latvia, I will use laser pointer. This is Latvian groundwater level times dataset, and as each horizontal line, it's a groundwater well, and we can see that in some time in the past, starting from 1960s up to 2020, we have some parts where there are some gaps, some missing values, and in some cases there are some missing values in multiple wells at once. And all these gaps actually are making problems if we want to do something more with our data and how to fill these gaps. And we developed the strategy how to use how to assess the performance of gap imputation performed by different machine learning algorithms. And the most successful algorithm was MISForest, which is basically based on the random forest algorithm. So the red part is cutted out part, which the model didn't see. And so we used machine learning to try to predict groundwater level in this missing part. And as you can see, the black line is the original data. In some cases, the model performed quite good, even though the gap is quite large, as you can see, almost 2 years of the missing values here. But in some cases, it didn't work that well. So there are different, in some cases it worked quite well, but not for all cases. And also we can use machine learning, or in this case, deep learning, to assess climate change impact on groundwater. And even as you can see, this is an article in Nature Communications Journal, which predicted groundwater levels for the 2100. So 80 years from now in the future. And what's interesting in this paper is that they used the convolution neural network approach, and they used only two input variables, precipitation and temperature. And they described that this model was so clever that he transformed these two variables to all the necessary data. For example, typically we are using evaporation, some kind of other, like a soil moisture, other kind of data, but this model somehow was able to squeeze out all the necessary information just from these two variables. So that looked quite nice. And then I promise that I will talk about groundwater modeling challenge, but I will start with another challenge which was performed 6 years ago. And it was called Karst Modeling Challenge, and this was the beginning. And that was a challenge where 13 teams participated and tried to predict spring discharge using different kind of models. But there were not only machine learning models, there were also the lumped catchment models and some I think even some numerical models probably. But yeah, but the catchment models actually performed the best in this challenge. But it was also followed by neural network models. And so the idea was that, yeah, every team had the same task, the same data, but they didn't see the right answer or the what is the right answer for the prediction part. And so it was quite interesting paper that combined a lot of teams, and there were different kind of outcomes. And one of the outcome or the result was the conclusion was that it was quite surprisingly that the models were not so good at predicting the base flow, which is basically when the spring is discharging water with a low flow. Basically low flow conditions. And here are some results from that challenge, where we can see that models are categorized in 4 different categories, and starting from some reservoir models and neural network models. And we can see that on the right part, the particular metrics of each of the team, or on each team use different kind of model. And that's for some teams, the performance was quite nice. And for some teams, the performance was not so good. For example, we can see that GRANDE-U model, which I showed, which was from France, actually was the winning model, which performed the best. While, for example, LSTM or long short-term memory model, actually, in this case, it performed quite bad. The Nash-Shockley coefficient is below 0, which means that it's a really bad model. And all these results are published in a paper. And now we come to the Groundwater Modeling Challenge from 2022. And this challenge was inspired by the Karst Modeling Challenge, which I just presented. And in this challenge, 15 teams participated, and only data-driven approaches were used. We were provided by with 4 monitoring wells from Germany, Sweden, United States, and the Netherlands. We had 15 years of training data, and we had to predict 5 years using explanatory variables. And the groundwater level was available only for the training part, but not for the prediction part. So basically, we could not see what is the right answer. So we were not. It wasn't possible to cheat. So in that sense, this was a fair game for everyone. Of course, you could try to find the raw data somewhere, but that will not be a good idea to do that. And the challenge was opened in GitHub, and all the submissions were also collected in GitHub. So all the scripts, all the submissions are still available in this GitHub page. So you can visit it and find all the submissions by all the teams. And most teams also submitted scripts. Also, I submitted scripts, and so you can see in this GitHub all the team submissions. And for example, if you will open my submission, which is called Team Jānis, then you will find my scripts and my results. And yeah, we were provided with groundwater heads for the calibration part, and forcing data for both calibration and validation part. And yeah, we were not allowed to use groundwater head or groundwater level as a predictor, as well as we could not look for any new variable to use. We were allowed only to use the data that was provided. So to make the rules simple for everyone, and to make all the models comparable in the form of, at least to make the performance of models comparable. And yeah, you can see in this lower graph, this was the part that was provided for us, these 15 years of the data, the gray part. And the colorful part is the validation part, which was not provided for us. So we did not know what are the right values, what are the ground levels in these parts. Only after the challenge ended, we could see what was the right answer, but up to that point, we could not see what is this, what levels were here in this colorful part. And these are the general results. We can see how each team performed for each of the wells. So there are 4 wells. Actually, there are 5 wells, but one was quite bad. One had bad results, so it was excluded from the paper. And we can see also, according to different metrics, and in this case, I have selected Nash-Sutcliffe efficiency score, how these models performed for each well. And we can see which team and which model were this winner for each of the wells. And one of the conclusion is that there's not one single team or not one single model that can make the best model for all the 4 wells. As we can see, the winners are all, for each well, there are different winners. And for example, I was winner for predicting groundwater level in United States. So quite interesting that, I was more successful in States than in European wells. And these are image from the paper, which in the next slide, there is a link to that paper. And here is the comparison for all the teams for different all these groundwater well heads. And eventually it was all these results were published in a paper quite recently in the end of the last year in the journal of in Hydrology and Earth System Science Journal. And here is a small table where was summarized how much time each team spent for each of the groundwater wells. And in general, the models were developed in starting from the less than 1 hour up to 19 hours. But in average, it was approximately 4 hours per well. So I will say that's quite fast. For example, in several teams, like for example, I created my code for one well, and then I just copied the same code for the rest of the wells. So it was much more faster afterwards. So you can find the paper also in this link. And now I will give an example of that well from the United States that I modeled the best. So of course we didn't know what is that well, where it is located, and what is the number of that well when we were in active phase of the challenge. But of course, after the challenge, we were provided with all the data, and also we finally get to know where that well comes from. And it seems that that well came from the I cannot pronounce that name, Connecticut state, from Mansfield town. And I even found the image on the USGS homepage how this well looks like and where it is located. And this is how the groundwater well level looks like for this particular well. And we were provided by several explanatory variables. Of course, we had some daily values, like we had date when for each row we had some head measurement, or that's basically we can say that that's groundwater level. And then we had the precipitation rate for each date. We had some temperature mean and temperature maximum for each date. We had evapotranspiration. In this case, it was a potential evapotranspiration. And we had a stage of the nearby river. And that's how, for example, precipitation river stage looked like. And this is the groundwater head for a small fragment of 2 years. And we can see that groundwater river stage looks that it correlates with groundwater head. But for the precipitation, it's quite hard to see if there is some relationship between groundwater head and precipitation or not. And if we go back to the roots of how groundwater is forming, then it's not that when the rain drops on the ground, then the water level is rising immediately. There is some delay, and there is some like a response time from the time when the rain drops up to the time when the water level is actually reacting to this precipitation. And that's actually the idea also behind the impulse response functions, like in this pastis package, that when the impulse is coming down, like there's a rain event, then the impact on the water level is actually going like that one. It's basically, it's like a function. And so in that case, it means that today's value of precipitation will not say much about the water level today. And that we could also see in the previous graph, and that's and how to deal with that. There are several approaches. We can lag the data or just shift the data to make the yesterday's value as today's value. But we can also use some rolling functions, and we can call rolling statistics. So basically, we can calculate some summarizing value or average value for the last few days, and say that this is the new value for today. And that's how I did. For example, this is just an example. So I took 5 days of five previous days of the river stage values, and just aggregated to one mean value and said, okay, today the value is equal to average value of the 5 last days. And I did it also for the next day and for the next day and so on and so on. So basically, you can see that's the reason why it's called rolling function or rolling statistics, that basically it's rolling through my data table and making new variables based on the previous ones. And we can do that for all the variables and for different length of the window. We call this rolling window. And I did it for 5, 30, 60 days, half a year, and almost and 2070 days. And for precipitation, potential evaporation, and infiltration, I used the sum function. So basically, I summed up the previous values. And for all the rest of the inputs, I just used the mean value. And this is an example. So if you are trying to correlate groundwater head with precipitation, we see that there is no correlation if we don't do anything. But if, for example, we are using this rolling function of the rolling sums of the last 2070 days, we can see that correlation goes up quite rapidly. And still, it's not the best like predictor, but we can see that no, this precipitation in that kind of form is much more useful to predict groundwater levels. And again, the same graph, we can see the original data is like event-based data. So in one day it rains and the next day it doesn't rain. But if we are using this rolling function, we can get much more smoother changes in precipitation. And if we look closely, we can still indeed see that there is some correlation with the groundwater head. We can see that actually it follows quite well with groundwater heads, what we can observe in this period. And so how I did it, as I said, all the codes are freely available in GitHub, and this is the specific link to my R script. So yeah, the difference between Vytautas code is that Vytautas code was in Python language, but I'm more used to work in R language, and so I made this. I participated in this challenge using R language. So yeah, this is how I imported my packages. This is how I defined my rolling functions. And then I applied these rolling functions to all the inputs. So basically we can see that I used these rolling functions that I defined here to make new functions, for example, for evapotranspiration, precipitation, infiltration, and also for the positive values of air temperatures. I used rolling sum functions, but for the rest of them, I used average value functions. And I also performed some multiple additional steps. Basically, we can call all this feature engineering. And all this was done just to make the data more predictable. And then I also used some cross-validation strategy just to tweak some hyperparameters. And actually, in my case, I used quite simple approach. I used the random forest algorithm, which I defined here. And I used already fixed values at the beginning, some number of trees and other parameters were fixed, but the only parameter which I tuned was mtry, so the number of features that is selected for the model. And so I use this kind of cross-validation strategy to tweak the number of mtry. And this is how this cross-validation strategy looked like. Like this black line is the part which is used for assessing the model performance, and the rest part is used to make the model. And I did it several times by sliding this prediction part in time. So eventually I got that every data point in this data set was used both in the calibration and also both in the validation part. And this is the result. Basically, I selected the best model and used the best model to predict the future. And the future looks like that one. This is my figure that created by me. But we can also find the same data in the scientific article, where my data is in the orange color. Because as you saw that my model was the best performing in this particular well, and indeed we can see that Nash-Shockley efficiency score is quite high, 0.994. That's really high, quite high performance. So yeah, if you're interested more, you can ask me or go and look on my script here. But what I wanted to say in my last slide is that there is a new challenge actually announced. It was announced last year, and it's called Groundwater Spatial Modeling Challenge. And this time, the organizers are all partly the same as previously. And the idea here is not to model groundwater levels, but as you can see, it's called Spatial Challenge. So in this case, the idea is to predict nitrate concentrations in Germany. So if you're interested, and I hope that you will be, and I will actually encourage you to be interested in this challenge, then please consider to participate. Actually, initially it was supposed to end by the last year, but due to low activity, and that's probably because of the more challenging data, or I don't know what, it was extended. So the new deadline is in the middle of the summer this year. Thank you.
How cool is that? Thank you, Jānis.
Yes, thank you.
Yeah, this is very impressive. Let's see if there are questions, because there was a lot of material and actually quite fast. So Anya, Tatiana, Justina.
Thank you.
I mean, yeah, there's a lot to unpack. I think we'll just have to go deep into this notebook from Vytautas, yeah, to see how everything works in each step. And probably then we will have some questions, but we will see how this works, because I told you, Vytautas, that we have a updated version of the data for the river runoff. So we will have to probably do it on our own, and yeah, we'll see how it goes with the stuff that you showed us today.
No
Yeah,
problem. We will help.
99% accuracy is very impressive. So let's try to make sure that it indeed is the case.
Yeah.
I
agree.
Because I mean, that's fantastic result. Because if we would not get this high level of accuracy, I would suggest doing something like what Jānis has done with rolling functions and spend some more time on feature engineering. But if we already have 99%, that's kind of pointless. So, yeah.
Yeah, basically, I will share that I'm pretty sure that the code I wrote is correct, but the spatial joining part, it was new for me. I've read the documentation, but still, it needs a thorough revision.
Yeah, so especially when you say the predicate equals overlap, that was a little suspicious because we would just need to look at geometries of those small polygons that you derive at 0.05 degree and see you know how they inherited all the values, right? And then take it from there. I think yeah, the overlap predicate is where I would see what actually happens. Because you see that there's a big drop in the number of cases, in the number of cells, from like 700,000 or so, or 800,000 to 1,500, or 150,000. Yeah, but even with this drop, the results look very good. So yeah, I would like to run it myself too.
Sure.
Yeah, and thank you for doing that. We are recording that, of course. So if it's okay with you, we'll just distribute that within this team that has been attending. I don't think we need to distribute it more widely at the moment, but unless you want.
I'm okay with the distributing, actually. I just had questions about the data. Can I use it to share? If it's okay, then I will add everything in one bundle and upload on our G Drive shortly.
So speaking of the challenge, the new challenge that Jānis mentioned, do we want to go for it?
Who, me? Yes.
I mean, maybe
everyone. But it's
When
quite
is
challenging. I looked at the data. This time it's really challenging, I think.
When is the deadline?
15th of July.
We'll have time.
I was actually thinking we can do our own challenge with data that we have, so then people predict for us.
Well, they provide the data, right? On which to do the challenge.
Yes, all the data is already available. Of course, you don't know where the locations are of these wells, where the nitrates were measured, and you don't know the right answers. Of course, there is a training data set, but there will be also some testing data sets for which you have only these explanatory variables, but not their nitrate concentrations.
Copernicus data portal has some nitrate data. Last I looked.
But in this case, you need to use only the provided data.
Yep. If you have a link to that challenge, can you paste it in chat?
Oh, yeah, sure.
Oh, great. Yeah, this is cool because challenges is always fun. Another thing that's something we started discussing with Jānis before the workshop. There are several kind of general Python geocomputing courses. One of them even from Estonia. And looks like this example that Vytautas developed could be kind of specialization of some of the general tools that they show in spatial data science in these courses for groundwater, and of course what Jānis is working on. So there might be a way to maybe connect with that team and say that we can expand on like geocomputation tools that originate in the Baltics and offer some specialized examples that are focused, let's say, on groundwater. That is, I mean, we don't necessarily need them, but they have some recognition and dissemination channels, and that's something we can use. So, of course, we need to talk with the Estonians about that. And Jānis also knows some of the folks there. Oh, we can win prize money. Yeah, on Kaggle, of course. Yeah. Kaggle is a very large competitions. Here, we're talking about maybe like a couple dozen teams. That's more manageable. Yeah, well, when it gets to spatial, we can look at some spatial models, of course. Any thoughts around the table of what else we can do, or additional models to try? Again, my feel is the first thing would be to just review the results again, and because this is actually quite important piece of work that Vytautas has done with this data, and I think quite worthy of papers and presentations, if the 0.99 stands especially.
Well, I just thought about not like modeling, but the features and their relation to the grades. What to expect? What accuracy do we expect? Because all of them are actually hydrological, some kind of features, except for grades. So it could be that high, but in other cases, it really needs review. So I'll be waiting for your judgments soon, hopefully.
Yeah. So you will share the notebook, right?
Yes, I will share it. I will add it to the bundle of the course material.
Great.
In any case, it is an example how to work on that. I will name it case study Poland. So I'm guessing someone, at least Poland team, is very interested in learning that. And probably someone from Ukraine would be as well. So yeah, we will probably then contact later, and if someone, well, now we are also managed to like push our database creation, so hopefully some data would occur in the following months, and then we can proceed with that. But now we're focusing on the Poland data because we already have something to work with.
Mm-hmm. And it's actually nice, small, clean data set to work with.
Yeah, it was my Absolute pleasure to work with that.
Yeah. Thank you, Anya. I guess you can.
Thank you.
Yeah. No problem. I'm glad.
Yeah, send us more. Yeah, like
All right.
100.
So I guess at this point, we'll just encourage everybody to try, set up Anaconda and run it on your own. And we can reconnect again and share impressions, or just do it by email.
Yes, maybe eventually we'll put that on some platform online to run the code there. But for now, I work on my machine, so I created notebooks for that.
We're exactly on time.
Really?
Thanks,
That's
everybody.
surprising.
Will we get the presentation from Jānis with all the links and stuff?
Yeah. I will. I don't know how we will distribute it, but sure. I hope someone will send you.
Yeah, we have our Google Drive space on GRANDE-U Google account, and also we have Google Sites website, so it all can go there. Or we can just keep everything on GitHub and just point to that. That may be simpler.
I think we have all the emails we can send out. Yeah. Maybe CT can send.
If people registered.
Yeah. If not, then we can keep on our Google.
Thanks, everybody. It's wonderful to see you, and thank you again, Vytautas and Jānis. That's been fantastic.
Yes, thank you, guys. It was awesome.
Bye-bye.
Okay.
Thank you.
Goodbye, everyone.
Thank you.
Have a
Bye-bye.
nice weekend.
Bye-bye.
Thank you.
You too.